Hello, and welcome to session 5 of our class. Today, we'll be talking about probability distributions, and this will really extend off the fundamentals we discussed in the previous class, where now we'll talk about measuring a random variable. We can think about a variable as continuous or discrete, depending on the range of values that it assumes. And discrete and continuous, we talked a bit about this when we were describing the different distributions where we had those intervals compared to a histogram. So some of these things should start to build off of what we've previously learned so far. In this chapter, though, we will focus on discrete random variables and their associated probability distributions. We'll be talking about Poisson distribution, hypergeometric, and some of the other aspects that revolve around this. Let's dive in. So just to repeat some of the concepts we've discussed, but in this lens, we're talking about discrete and continuous features. A discrete random variable assumes a countable number of distinct values compared to continuous, where we have uncountable, and there is this range of values between an interval. For example, there is a discrete number of customers that are surveyed in each sample. The number of customers would be considered a discrete variable since it's countable. You have individuals that can be binned using whole numbers. Compared to something continuous, such as the average number of customers over time. This is something that might not be a whole number. If you're taking the average, you might have decimals and more numbers between whole numbers. So that's what we're talking about when we think of continuous versus discrete. And we'll calculate summary measures for these variables using the mean, variance, and standard deviations. And these measures are valid because of the nature of random variables. This we touched upon a bit when we talked about the law of large numbers in the last lecture, talking more about this. Life is uncertain, talking about randomness. How do we make decisions in the face of this uncertainty? We can measure this level of uncertainty by the term of a random variable. Let's think about the phrase, a simple random sample was taken. What does this actually mean? We use randomness to assure that each sample is independent of each other or that they are unbiased, where each sample has an equal probability of being selected. Additionally, we assume that because it's random and we take a large enough sample, that eventually we'll start to recognize the true tendency of the population. This touches on the central limit theorem, which we will get to in future chapters. But for now, we consider that random variables allow us to measure the likelihood of an event occurring, given that they are independent of each sample and represent the best approximation of likelihood. So when we're talking about the mean and variance and standard deviation of a sample, our goal is, because we're taking this random sample and having a population large enough, we can start to inform what the larger population would look like with some degree of certainty. We touched upon this in the last chapter when we talked about this Plinko probability, where I first thought 6 would come up, but we saw when we took an individual sample that there was variance along this probable output. But once we ran many samples, we saw this type of distribution that would align with our expectations of where would the ball likely land. This simulation represents the probability distribution of a discrete random variable of each sample or ball in this case. This provides the probability that the random variable X will assume a particular value. In the Plinko case, the likelihood of a ball will end up in one of the middle bins. We can also define this random variable in terms of its cumulative distribution function, or how many values will be within a certain range, such as the likelihood of a ball dropping in the first 6 bins. Two key assumptions of discrete probability distributions is that each value has a probability between 0 and 1. Second, the sum of all probabilities will equal 1. This is for any probability distribution. And that allows us to look under the curve that would be created by that distribution, or the area under the curve, and know that all of those different probability distributions below the curve will equal 1 when we sum them together. And this allows us to use these distributions to make some type of informed understanding of the probability of a Plinko ball landing in the first 6 bins compared to the middle 6 bins versus the right-hand 6 bins. So we use these types of distributions to understand how patterns might exist in this distribution of events. And our analysis of probability distributions is used so we can calculate the probabilities associated with different values that the random variable can be. This allows us to calculate the summary measures such as mean, variance, and the standard deviation. One of the most important things that statistics can provide us with is this expected value. This is used to say that what's the likelihood of seeing a certain outcome given the distribution of random variables. This expected value is referred to as the population mean. In our Plinko example, we can think of the population mean as being the average outcome of where the ball lands. This usually is where the ball lands most often, or right where this vertical line is. This is the central location of the distribution, but we don't know how the values vary from this central tendency. The balls might fall very far away or tend to be close to this value. And we use the measures of standard deviation and variance to indicate whether the values are clustered about the mean or widely scattered from the mean. These different measurements can be calculated using statistics and math to see what is the average value. How much do the other measurements vary from this central value? And to what degree is there deviation? So in our last module, we talked about some of these different summary statistics using the mean and variance and standard deviation, which looks at how far does each value compare to the average. So we know what is this range of distribution for our sample of random variables. Let's talk about how we calculate this. Using an example from the textbook, we see the probability of performance and the amount that would be expected as a bonus for each level. This is just a little case study trying to understand what would be the average value that employees would earn. So we want to know what is the probability of performance and the amount that would be received as a bonus for each level. So given superior, good, fair, or poor performance type, what's the probability that you would earn one of those? And then you would know the likelihood of receiving a bonus given your performance evaluation. So the way we would calculate this is we first multiply the probability of an event occurring by the value. In this case, this would be the dollar amount. We add up the amount for each probability and the amount that would be received to calculate this central value, or the average or mean. So the second column here shows that the average bonus will be $4,200. Some will earn the $10,000, others $6,000, and others won't receive any bonus. But our mean shows the long run average for all the employees. Now let's calculate the variance. You want to know what's the likelihood that you might earn somewhere near this average. Is there talking when we discussed around income in the last module, saying if Elon Musk walked into the room, this would totally disproportionately skew the mean. We want to know how common do these values exist and what is the variance between these values. So we take the difference from the mean and square it, because this shows how far away that value is from the mean in terms of absolute value. If one employee receives the $10,000 bonus, how rare is that compared to the average? Well, to calculate this, we would take the square difference to account for this distance, and we multiply it by the probability of this outcome even happening. Then we add all outcomes together, and this equates to the variance. in order to obtain the standard deviation, we simply take the square root of the variance. And this essentially undoes that the square difference, and that brings the values back to the original form of unit. So that's why when we look at standard deviation, we can interpret it in the same value as the mean compared to variance, which is a little less straightforward to interpret. So the average bonus would be $4,200, but an employee might expect to receive about $3,000 above and below this value. And we calculated that by using the variance and standard deviation. An intuitive way of thinking about standard deviation is that it's a measure of spread. So we need to say for every value in the data set, how far away is it from the mean? If we simply added up all the differences, we would get 0 because they would cancel each other out because some are above, some are below. So we want to give equal weight to the differences that are positive as well as negative. And that's why we take the absolute value, which negates any positive or negative. Unfortunately, the absolute value doesn't play well with calculus, since eventually we'll want to minimize this spread when we fit a line and thinking about derivatives and more of the actual computational side of it. Absolute values are more difficult to work with. So the function gives equal weight to both positive and negative, but is also easy to differentiate, or when you're taking different integrals and more of the calculus side of things. So the simplest function is to take the square of each difference. Then we take the average of the squared differences, and that is the variance. Then we can easily scale back to the size of our original data by taking the square root, and this is the standard deviation. So this explanation just gets into the math behind why we are doing the formula we are doing by taking the squared compared to taking the absolute value. And really this just allows us to then easily compute these different area and distributions under the curve. But in a nutshell, the larger the variance, the farther away from the mean the values will vary. And the smaller means that the values are very close to the mean. If we want to measure behavior or potential outcomes under uncertainty, we can use variance and standard deviation. This answers the question, why does this matter? Why should anyone care? So thinking about something like a consumer's choice, there might be uncertainty in the future value or outcome of a risky purchase. We can think about these problems using statistics to break down the likelihood of different outcomes and then weigh our options. This also relates to something like portfolio returns, where we talked a little bit about this when we compared growth versus value of different funds. If anyone asks you for investment advice, my first response is, what's your level of risk that you're willing to take on? I'm personally risk adverse, but different types of experiments have different types of risk, and thinking about how we can start to measure this level of risk using statistics. So the rest of this chapter, we will discuss the binomial, Poisson, and the hypergeometric distribution. First, we will focus on the binomial distribution, and the conditions of a binomial distribution fit the Bernoulli experiment. And what is this? This was named after the Swiss mathematician, James Bernoulli, and the process consists of a series of independent and identical trials of an experiment. Each trial has two possible outcomes, either success or failure, and we can represent yes, no, true, false, success, failure using 0 and 1. And the probabilities remain the same from trial to trial. So I like this little visualization. I'm going to refresh the slide so you can see from here how the probability between these distributions change as the likelihood of a success rises, the likelihood of failure goes down. So these things counterbalance each other and they're mutually exclusive. You can't have both success and failure in these types of experiments. let me get back to presentation mode. Alrighty. So first we'll focus on this binomial distribution. And the other distributions we'll talk about are somewhat similar, actually, as we approach how to use these distributions to calculate any type of certainty around likelihoods. So this approach of using a binomial, or this Bernoulli process of independent and identical trials of an experiment, is valid for any type of experiment with binomial random variables. And what this means is something that has a yes or no answer, such as if a customer will default on a loan or not, test results from a new drug being effective or not effective, and so on. Our goal is to attach probabilities to various outcomes of a Bernoulli process. And the outcome is this binomial distribution. The textbook took an interesting approach of constructing a probability tree in order to illustrate the possible outcomes and the associated probabilities. This can also relate to, if we wanted to get into some more advanced concepts around machine learning, it's actually kind of similar to a decision tree, where you would have this bifurcation of classifying an outcome based off of these little decisions of yes, no between different variables. So we would have this type of tree approach to know the probability distribution and how frequent does this outcome occur. So in our case, think about this tree as how we know if an outcome will happen or not. We can think of all the different samples we take, and similar with last class when we talked about probability of having a girl and a girl for children, this is a similar concept. We're just visualizing it in a different way. So let's go through an example of how we can generalize this probability distribution. For example, in this little case study we'll go through next, a manager of a department store knows that 85% of her customers will use a credit card to make their purchase. Suppose 3 customers are in line to make a purchase. Let's construct a probability tree to then visualize the probability for a customer using a credit card. We can then add together the different outcomes to calculate the probability. So we see here in this tree, S and F are those different outcomes of using a credit card or not. And we want to know what is the probability that all 3 customers in your line will use a credit card. And so similar to this, the question that we went through last time, you can list all the different combinations, where the first one, SSS, would say all 3 customers used a credit card. And what would be the probability? We would multiply that 85%, saying there's an 85% chance that a customer will use a credit card, and multiply it by 3. So we would have that probability that all 3 customers use a credit card to be about 60%. Next, if we wanted to say at least 2 customers used a credit card, we could then look at any combination where it doesn't matter if the first 2 or the first and the third, or if the last 2 used a credit card, because if our question is just at least 2, it doesn't matter the order. But if we had some type of order importance to say what's the likelihood that the first 2 customers use a credit card, then these differences would matter. So we would multiply the likelihood of using a credit card, which is 0.85, and then what's the likelihood that they don't, to account for the not using a credit card, which we would simply subtract 0.85 from 1, which would bring us to 15. And then we multiply those probabilities together. And since it's the same, depending on if the first and the third customer come in, where we see right below this, we would just change the multiplication order around, but it doesn't matter when it comes to the outcome is the same value. Thinking about when the probability is just one customer using a credit card, we take this similar approach of taking what's the probability of this happening and multiply it by the number of samples we take. And this is what this probability tree is visualizing and allowing you to then calculate at the end. But let's talk about a formula that breaks this down and we can now use to calculate this. And this is the following formula for calculating this binomial distribution, where we have P and Q, which is just those two sides of the coin, where probability of getting a success or true or one, however we want to quantify what true or false is for this two sides of the coin. And Q is the probability of getting a failure or zero or false. All these things are synonymous with each other. But just think P means true, Q means false in a simple sense. So we take these different probabilities and we take this factorial on the top to go through all those different combinations. And then we divide it by the number of trials. And we also take these factorial, and this will then create this type of probability of knowing the likelihood of seeing a success. So we use the factorial to show the other options for number of successes. We don't need to include 0 factorial. If we wanted to actually start from 0, what's the likelihood of all 3? We don't need to calculate 0 since that equals 1. So in this case, there are 3 sequences having exactly 1 success. And we can verify this with our probability tree that we went through. Now we're trying to calculate what's the probability that all 3 customers use a credit card. And thinking about the second part of the equation, when we go back showing this, of that P, the slide's not moving quick. This talking about that P times Q on the second half of it. Let's talk about what that means. The second part of the equation, P to the X, I'm just gonna wait for it to move. Okay, P to the X times 1 minus P to the N minus X represents the probability of any particular sequence with X successes and N minus X failures. Thinking back to the tree, in any order of success and failure, we can obtain the probability of 1 success in 3 trials by looking at the rows with only 1 success in it and 2 failures. We then multiply the probabilities to obtain the chance of the entire sequence. For the sequence consisting of only 1 person having a credit card is a 1.91% chance. To obtain the overall probability, we multiply the binomial coefficient by the probability of obtaining the sequence, which would be 3 times 0.0191, which equals 0.0573. So by taking these different outcomes and multiplying them together, we can then start to see what's the likelihood of this happening. And we can use this formula to calculate the mean, the variance, and the standard deviation for any binomial random variable. For the mean, we take the probability of success and multiply it by the number of samples in the experiment, n times, or like how many samples did you take? So on average, we expect n times p successes. For our example, since there is a probability of 85% of having a success or having a customer use a credit card, we multiply this by 3, which is 2.55. And this could be interpreted as, on average, for 3 customers, 2.5 will have a credit card. And this ties back to what we introduced this chapter, talking about this continuous. This isn't discrete saying 3 customers. We're now saying on average, 2.5 out of 3 will have a credit card. For variance, we use the mean and multiply it by the likelihood of not having a credit card, which is 1 minus 0.85 or 0.15. We multiply 3 times 0.85 and then multiply by 1 minus p to equal 0.38, which means the number of customers with a credit card might vary from 2.55 by 0.38 more or 0.38 less. And this gets a little more difficult to interpret, thinking about, more than 2.5 will have a credit card and a little bit less than 2.5 is this type of variance. For standard deviation, we take the square root to bring back into the same data value of persons, which makes it a little more contextual. So the likelihood of all 3 patrons having a credit card is 0.255 with a standard deviation of 0.62 of a person less or more. So now let's dive into using Python to calculate some of these things. And this will be very similar to what your homework will look like. So we'll be going through a different example compared to the credit card, but it'll follow a very similar format. And in this module today, I'll be hopping back and forth between using Python and the slides as we move through the different distributions we'll be talking about. So in this whole lecture, we'll be talking about binomial, Poisson, and the hypergeometric distributions. So first, what we just talked about in the lecture was this binomial distribution. And let's go through this example of, in the United States, about 30% of adults have a 4-year college degree. This was just a statistic taken from the Census Bureau in 2018. Suppose 5 adults out of this population of all adults in the United States are randomly selected. You want to know what's the probability that none of these 5 adults have a college degree? Also, what's the probability that no more than 2 have a college degree? What's the probability that at least 2 have a college degree? And then we can use these types of distributions to calculate the expected value, the variance, standard deviation of this binomial distribution of college degree or not. And we can use our data visualization skills to depict this probability distribution and comment on how the skewness might look like. So whenever we're working with these types of questions, it's very helpful to define our variables and try to stay consistent with using the symbols based off of the formula. So we talk about n, which is usually used to define the sample size. So in this case, we took 5 random adults in our sample. P is the likelihood of success, so true or 1. So our probability is 30% of adults will have a degree. So likelihood of degree is 0.3, and then likelihood of not having degree is just 1 minus 0.3. So we'll run these to define them. So now we can work with these different values. And I created a little function. Let me make a note for what this function does, because it inputs the variables. And it takes that exact formula we talked about with, you take the factorial of all the different samples and you divide it by the value you are looking for. So in this case, the first one of our question, the likelihood that no adults have a college degree out of these 5 that we sampled. So we'll say our value is x of 0. We want to know 0 outcomes being all false or all true, actually, in this case. And then we times that by the factorial of n minus x. And then that second term we talked about is applying then the probability of a success or failure in this case. And then we output the multiplication of these 2 sides of the formula. So just to go back to in our slide, that function just outputs this portion of n factorial over the denominator. That's the first portion, and the second portion is this p times q. And that is what this function will return, is that output. So the tricky part is knowing what you should put in for x. But in this case, this one is relatively straightforward, of saying 0. What's the likelihood none of these 5 adults have a college degree? And using our function we just made, we can now input our different variables, and we see that out of 5 adults, there is about a 16% chance that none of these 5 randomly sampled adults have a college degree. Which makes sense to think about if 30% of adults, and we take 5 of them, that the likelihood that none of them have a degree should be somewhere within this range. Next, if we wanted to say the probability of no more than 2 having a degree, we would need to take this same function and apply it to the different options of saying no more than 2. So we need to think no more than 2 would include 0, 1, or 2. So we then add up these different probabilities to say no more than 2 have a degree. So this could mean that only 1, or this could also mean 0. Similar to that decision tree, we would add up those different options that would then output the result of what we're looking for. And that's what I'm saying by saying that that's a tricky part here, is knowing how we manipulate these things to actually answer the question we're after. So we add up the probability, thinking about what would it take for us to complete this requirement of saying no more than 2. And so out of a random sample, we see there's actually an 83% chance that no more than 2 will have a college degree. And we add up these probabilities that no one has it, that 1 or that 2 people have it. So it's actually a pretty high chance that just under 2 of these individuals that we sample will have a college degree, which again kind of makes sense thinking about what we started with, that probability of knowing 30%. Next, let's talk about the next item we want to do, which is the other side. What is the probability that at least 2 have a college degree? So now we take that other side of saying at least 2, which means that the floor would be 2 have it, but it could also mean that 3, 4, or all 5 of our adults that are sampled have a degree. So we just take that other side, we use the same formula and apply it on how many samples that would result in having a college degree. And we add it all up. So now we could say there is a 47.18% chance that at least 2 of these randomly sampled adults will have a college degree. And that allows us to answer these first 3 questions. Next, we'll move on to calculating the expected value, or the mean, the variance, and standard deviation. So we use our formula that was defined, which just takes the probability of success times how many times you're going to take this. So out of 5, or I can even make this a little bit more flexible, for whatever sample we want to take, the average number of adults with a degree will just be NP, which is N times P. So now this gives us this understanding that out of 5 randomly sampled adults, about 1.5 of them will have a degree, which aligns with some of these different probabilities we were talking about when we wanted to calculate it for a specific number in mind. Next, we'll use variance, which again, I'm just plugging in those formulas and using our variables that we're working with, which now we take the mean, which we had here, and I'm just using that again here, and we multiply it by the probability of 1 minus the chance of success. So we can think about the variance will be 1.05 adults squared, which is difficult to think about. So let's use the standard deviation, which just takes the square root of this And now we can have the same unit of saying this will deviate about by 1 adult. So on average, we see 1.5 adults, but because of the distribution of having this 30% chance, we can expect maybe 1 adult more or 1 adult less, depending on the sample you take. Rather than using our manually created probability formula that I just used from the formula we defined, Python also has this handy function from SciPy, which creates this binomial distribution. And we can then use that for calculating more of these different summary statistics. So if we didn't want to use the formula, we can start to use the actual distribution that we can simulate using Python. So in order to make our research reproducible, as we talked last time, it's important to set your seed, which I don't think I need NP there. Don't know why that was there. Okay, so now we have our seed set, and therefore anytime I run this, because this function that I just talked about from Python will just create this random distribution, a discrete random variable of classes. It'll create that binomial distribution based off of some of our inputs, and will make that distribution. So we need to set the seed to make sure that that distribution will be consistent if we were to reproduce this. So for now, I'm just taking a sample of, let's have what R values is showing us here. This is breaking down what we just talked about and saying if 0 of our adults had it, if 1, if 2, if 3, if 4, or 5. That's what we're inputting here of R values. And by using this function of give me a distribution of binomial and saying for each value of 0 through 5 in this R values list, just calculate the probability given the sample size, which we defined before being 5, and the probability of success, which we defined before as being 0.3. And just by doing this, we now have the probability for each one of these individual outcomes happening. And this is equivalent to what we computed using our own handmade formula, and we just added these together. So in that first example of saying under 2 adults having it, we would then add together these 3 values. So these are equivalent. We're just now using Python's built-in functions rather than creating our own. And if we wanted to take the sum of all of these, because it should all equal to 1, I think it's kind of interesting that it equals just below 1. And this is mostly because of thinking about that area under the curve, that it is continuous and is asymptotic. So it never actually reaches the x-axis because it goes on to infinity. So that's why we say it adds up to 1, but really there's kind of like this very, very small piece that's missing. But really this all adds up to 1 if we were to think about it kind of in practical senses. But in mathematical senses, it's just not 1, but pretty much is. So if we wanted to visualize this, now we have the probability for each outcome, and we have the likelihood. So now we can visualize this using a histogram, or actually this is more of a bar plot since it's a discrete counting. So we can say the likelihood for each outcome that there is about a 0.16% chance from here that no adult has a college degree, but we see it rises that it's most likely that at least 1 will at 0.35%. But if we say at least 2, it goes down a little bit, and saying that all 5 of them have a degree is actually very low in likelihood. So this allows us to understand the symmetry and see that this is positively skewed, so that most of them are around 1 or 2 of a likelihood. So just want to say that if the success of failure, the probability of success or failure is equal, so think about flipping a coin. What's the likelihood of seeing a heads or tails? If it's a fair coin, it should be 50-50. We will start to see a normal distribution start to show. So we can say for here, this just to show that type of outcome of this cumulative distribution function. All right, so now I will return to the lecture and we'll talk about our next distribution. Which is the Poisson distribution. So when thinking about probability, we will have to talk about this Poisson distribution, which was named after the French mathematician Simon Poisson. Poisson worked on mathematical basis of wave theory, acoustics, elasticity, electricity, and heat, which is kind of interesting how there could be a common thread between all these different concepts. And the equation of probability had a lot of applications to measure the number of events within a certain distance, area, or volume. It's used to predict the likelihood for a number of occurrences over a specified period. This is particularly useful for questions about cues or lines or the rate of an event occurring, such as what is the probability of an electricity outage for the next year? And I bring that up just because I work a bit now with utility companies, and that's something that a company would want to model so that they can then know how can they mitigate these risks. But before we get into the Poisson distribution, let's cover some of the assumptions of a Poisson process. First, we have parameters for a time or space interval, and this ranges from any integer between 0 to infinity. We can't think of negative things happening. You can't have negative people on a queue, or in this example of how many cars would you expect to see in 10 minutes, you can't have negative cars going by. Our second assumption is the number of successes counted are independent in any non-overlapping intervals. So yesterday's car traffic is independent of today's car traffic, as long as there's no kind of lingering trends. So maybe that one actually in real life, there might be some type of dependence on today's traffic compared to yesterday, but thinking of something that each sample is independent of the last one. Last assumption is the probability of successes in any interval is the same for all intervals of equal size, and it is proportional to the size of the interval itself. So because we're taking the rate over a time or space interval, we can consider the scale across each interval since it is a proportion. So we aren't comparing the miles of car traffic, we're counting the number of cars per hour. And because we're using this proportion, it abstracts it from any of these individual units, because we're saying by hour, this is how many cars you would expect. We can now start to compare hours. So similar to the Bernoulli process, we think about the probability of an outcome. The difference with Poisson is we now think about the likelihood of success or failure as a rate. So instead of having a credit card or not, we're thinking, what's the probability over 3 customers that you will see someone with a credit card? So we're thinking about this more abstracted and saying as a rate of time, you need to have this interval constrained by some aspect of time or space. So we measure the probability of this event as a constant mean rate. And that rate is the really important part here. And that's how this differs from binomial, is that we're talking about a rate. So the formula looks at the mean number of occurrences during the interval multiplied by Euler's constant, or E, which is the natural logarithm. And we have Euler's constant because the Poisson distribution is a limit case of the binomial distribution. And if we think back to the binomial distribution, consider the mean here to be equivalent to number of sample times the probability. And these are the binomial coefficients for a fixed interval if we pass the limit as number of trials that could go to infinity. And we use Euler's constant as this to limit the constraints, since the number of trials that grow, the constant should stay the same. So we essentially use this to kind of limit that rate into not infinity terms. So that's why we use Euler's constant. And it comes up in a lot of different formulas, and it's kind of interesting how it relates to other things in life. But for now, this is the formula for what a Poisson distribution would look like. And we see these lambda symbols, which I will get into next with what that actually means. But for now, think of it as that rate of time. We can use the following formulas to calculate the mean, variance, and standard deviation. One thing to note is that the mean of the Poisson is equal to the variance, which makes it easier for us to solve. But this is because we assume that the rate is constant over the interval we are calculating for. Let's consider the number of outages for an electric utility company. We can say that there are 5 outages per month. We assume this is constant every month. If we divide the number of months into shorter intervals, such that each sub-interval contains at most 1 outage, now the probability is an interval similar to flipping a coin. If we assume the probability to see an outage in this tiny sub-interval is extremely low, then the probability of the event not happening approaches 1. Since the variance for the Bernoulli distribution is p times 1 minus p, and p is extremely low, then this would approximate the mean of lambda times the interval size. And I have a link here that talks a bit more about why we can use mean being equal to variance. Let's talk about how we calculate these things. Consider the following example. You are a manager at a local Starbucks, and you need to know how many staff are required to man the store. We want to know the probability of how many customers you're expected to see, because that would inform how many of your staff you should have on deck. We will think about the probability of a customer coming to your store over a 30-day period or a month. So as you're creating the schedule for how many employees you need, we'll think about it as a month. And we will assume this is just given your subject matter expertise as the manager of this local chain of knowing that the typical customer will actually come to this store 18 times out of a 30-day interval. And now we can start to think about the rates. So given that the rate of 18 visits over a 30-day period, we can say that the mean is 18 visits. To calculate the mean for a 5-day period, we would divide the rate by the proportion we're looking for, which is 5 days. So if we reduce the fraction of 18 over 30, we will get 3/5, or a probability of 3 visits per 5-day period. So this now helps us to know for this week, how many people would we expect to see? And therefore this week, how many staff should we have on schedule? So we can say that there is a probability that your customer, the typical customer, will arrive 3 times out of 5 days to your local store. Next, let's try to calculate the probability that a customer visits the chain 5 times. So think each day the customer comes in and buys their coffee. So all 5 days we have success or true again. So thinking about 1 is the outcome. We would plug this value of 5 into the formula And now using our mean rate of 3 to calculate that there is a 10% chance that a customer will visit the chain 5 times within a 5-day period. So this is someone who comes in every day for their coffee, and there's a 10% chance that they will come in every single day. Let's use Python to calculate some other probability questions a manager might need to consider when creating a staffing calendar. So moving on to talk about Poisson, we have our formula here, which again, it just mirrors that formula we defined in the lecture, where we have Euler's constant squared to the negative rate of lambda times lambda squared, lambda to x. And then we divide it by the factorial of whatever value we're looking for. So we define some of these inputs where for lambda is that rate times the interval we're looking for, which is 5. So our rate is 18 over 30, since that is what we defined in the beginning, saying every 30 days, someone comes in 18 times. But now for the interval we're after, for 5 times or 5 days, we would multiply this to get our lambda of 3. And now because we have the rate and we are looking for a 5-day period, we would plug this in, or 5 is our x. So for all 5 samples, think even to our adult example of the college degrees, that all 5 days, or to the last example, all 5 adults will have coffee or would have had a college degree in this sense. But now we're thinking it over like a period of time. So I don't know if that made it a little bit confusing, but just thinking about how we plug these different numbers in to calculate these different probabilities is what I was trying to explain there. So this is for all 5 days someone comes in, and what we talked in the lecture slide just a moment ago was that this is about a 10% chance that someone will come in every single day over a 5-day period. Now let's talk about what's the probability that a customer visits the chain no more than 2 times in a 5-day period. So now we think no more than 2, and that's why I bring up with the last example when we talked about binary, that we would simply just add up these different likelihoods together to know an answer for what's the likelihood that a customer visits no more than twice in a 5-day period. So it's about 42% chance that someone might come in only 2 times in a 5-day period. And we can use this function in Python to talk about this cumulative density function, and we would input the same value. And cumulative, this is something to be careful about if you're using the SciPy's package, that CDF is different than PDF, where PDF is just this point, and CDF is this cumulative distribution. So this does the heavy lifting of saying 0, 1, or 2. And it adds it all up together given the rate we defined. So this is equivalent to that. Next, if we wanted to talk, what is the probability a customer visits the chain at least 3 times? This is kind of an infinite likelihood. A coffee lover might come in more than just once per day. They could come in breakfast, lunch, dinner. So we want to think about this in a different sense, where we want to actually subtract those values that we just calculated, of saying the contrast of less than 3, or at least 2 times, and we would just simply subtract that from 1, because we're thinking about that area under the curve. And now we want to think about everything that's not the first 2 times. So we would take what we just did to calculate the opposite, which was no more than 2 times, and just subtract that from 1, which would provide us with a 58% chance that a customer will visit at least 3 times in a 5-day period. And so this could mean that they visited 70 times or just 3 times. We can also then use Python's probability distribution function, and we feed in this interval and say for all of these values, now see here we have this PMF, which if you go here, the probability mass function for all these intervals given the lambda. And now we can sum this up to 1, which this gave us the below more than 2, 0 to 2. And now we can just subtract from 1, and that gives us the other side. So I just wanted to show you how we can use the formula so you understand what's going on under the hood, but that also there is these probability mass functions and cumulative functions to be able to calculate the same thing. Let's think about what this might look like to visualize over the 5-day period. I gave a wider interval of 9, just so we can start to see what that might look like outside of this. So we use the Poisson function from SciPy to create that probability mass function. We create our canvas. Let me add some more comments here, just so some of these things look a little bit more familiar from last time that we talked about visualizing. Plot the interval, which is 0 to 9 against the probabilities. And now we can start to see this bigger picture of knowing that about 2 to 3 customers will visit within an 8-day period. So we see this positive skew again, that there's a low chance of a likelihood of more than 5 visits. So if we thought that silly example of just saying they came 70 times within a 9-day period, that would be super low likelihood. But you could expect that anywhere between 1 to 4 times that week has a decent probability of happening. So thinking again that it doesn't exactly equal 1 because it'll just approach, the area won't equal 1, it'll approach 1 because it'll just get infinitely more close to 0 as we extend the number of visits. And if we sum that all up, it'll get very close to 1, but never exactly reach it. And that's what this shows, where now you don't even see any line going up. It just pretty much is just a little dot of if we had this go now to even 14. So the likelihood really is within these confines of 0 to 6 times. Next, if we wanted to visualize this as a histogram, rather than having these different bins, we can use this function, which is, it just creates this random distribution given being a Poisson function, where we set the average of 3 and we say, give me a size of 10,000 examples. We can start to see a similar output. So this time we didn't even say what's the rate. We just said on average 3, and we're looking at all of these different possible outcomes given this distribution that we define, which is X. So if you wanted to just see what is in X, it'll be a very long list of this array of saying the likelihood of someone coming to the store. So think about this with that Plinko example of it's creating a simulation of what the output will be. And then we're just creating a histogram of all those outputs. And we start to see a similar pattern emerge where between 1 to 6 is really where the likelihood of someone coming in, but mostly it's between 2 to 4 times out of this range. All right. Next, we'll move on to the hypergeometric distribution. And we use this for when the probability of events are not independent. So thinking about those cars being independent, of each other, like the traffic of tomorrow is independent of the traffic of yesterday. But if we kind of think about that in a truer sense, maybe it's a little bit more independent on what happened yesterday. Maybe there's a bad car crash and things are still finding their way out of that. But thinking about hypergeometric would be valid when the probability of success changes from trial to trial, depending on what already happened, where the Bernoulli process is only valid when each sample is independent of the last one. So we can use the hypergeometric distribution to do when they are dependent on each other. And when we say they're dependent of each other, on each other, this would be appropriate for any sampling case without replacement. Kind of a more kind of in a box example compared to the cars, which kind of has a little bit more nuance to it. Think about just an example of having an urn full of balls, and we draw a white or black ball, but we don't put it back in the urn. So without replacement. So the likelihood of ball color depends on what has previously been drawn. If you've taken out all of one color ball, the likelihood of seeing the other will go up. So similar to if you play blackjack or poker, the probability of what card will turn up depends on what card has already been seen. So if you wanted to count cards, that's because each outcome is dependent on the last one. They're not totally independent. We can also ignore the dependence of events when the population size is very large relative to the sample size. So then we can mostly use the Poisson is really what I'm saying here. The hypergeometric, I want to talk about it just because I think it's interesting mathematically, but in real life, it's not usually required in a lot of different cases. So for example, because of this large population size, making it fair to still use the Poisson process. So for example, if we are drawing balls from an urn and it had 10,000 balls in it, of which 10% or 1,000 are black, even though we're drawing without replacement, because there's so many balls in this urn, the probability of success between draws is still valid to consider as binary. Since there are so many balls to choose from, it's essentially independent of each other. But let's break down the formula. The first term in the numerator represents the number of ways that X successes can be selected from the population. The second term here represents the number of not successes can be selected from the population. And the denominator represents the number of ways a sample size can be selected from the population. So really, we're just trying to account for all the different combinations again. This is just thinking about it in a different sense. We're running through all the probable outcomes and dividing by the total number of possible outcomes. And this is what accounts for the lack of independence between events, since the probability will depend on what has already happened. We have different formulas for measuring the summary statistics compared to the Poisson, where S is the number of successes in the population and N is the size of the population. And we will go through how we calculate some of these things next. So let's talk about another example. What is, you are in charge of making sure all of the shipments that come to your warehouse have a high quality standard. So you need to make sure that any defective products have been accounted for and that the rate of how many shipments that come in are not defective. So you're the manager, and in order to do this, you don't want to open up every single box and count everything. So you take a sample of just a few boxes. So let's say you take one box containing 20 units and we randomly inspect 5 units. What is the probability that exactly 2 of those units are damaged? So let's just say you establish this threshold that you will only accept this shipment if in this random sample in this box, since you don't want to open up all the boxes because that would be not very time sensitive to what you're doing as manager. So you set a threshold of quality control to say, as long as no more than 2 units are damaged in the shipment, we'll accept this shipment. And this is now what we can use to calculate that likelihood. So let's think about these products being something like mangoes. So let's think about the probability that 1 out of 5 mangoes is damaged. We can plug this into our formula where x equals 1. We take the factorial of the different potential outcomes, where the first value shows the different outcomes to be damaged. The second value calculates the probability of the mango not being damaged. And then the denominator is all the possible outcomes. The output is the likelihood that exactly 1 out of 5 mangoes are damaged, which is about 40% chance. If we wanted to calculate the probability that 1 or more units is damaged, we would sum the probabilities of x for 0 and 1 and subtract that from 1 again, similar to what we just did with the Poisson distribution, utilizing the probability distribution area under the curve equaling 1. So let's go back to Python and start to calculate the summary statistics for this type of question. So we're talking again about these mangoes in your shipment, and we want to know the probability that 1 out of 5 units in this inspection are damaged. So we define our variables, where now we're using capital N, where we could have used lowercase n for our number of draws we'll take. So that's why we use capital N, because that's the total number of items, where lowercase n is now this sample size that we're taking. So we're staying consistent with n lowercase, meaning the sample, where n uppercase is essentially the population in this example. And S is the number of successes, or the number of times that you actually see a damaged unit. And this function just plugs in all of those different formulas we talked about, where we're dividing the factorial by the different values and accounting for all the different combinations. So it breaks it down into the different terms that I talked about in the slides. So I encourage you just to think about the math that's going on under here. But at the end of the day, it's really just trying to calculate the different probabilities given all the different combinations. So first, let's calculate the probability that 1 out of 5 units used in the inspection are damaged. And I need to define my variables here. That's why I got this error that S is not defined, because I didn't hit run for the computer to learn what S means. And it had N from the last case study because it remembered N from the last time we defined it. So be careful when you're doing the homework. If you're doing things out of sequence and you saved a variable previously, make sure that it's a new variable or that you assign it to the right number you're calculating in the next one. So if you use x equals 1 for homework question 1, and you're using x equals 20 for another question, just make sure you redefine these variables. Otherwise, you'll be having inputs that aren't correct. So we can say the probability that 1 out of 5 units in this inspection are damaged, and that's about a 40% chance, which seems kind of high. We can also then use another function from SciPy, which is this Hypergeometric, which we just would input all of our different parameters, and we can say dot this probability mass function of the value we're looking for, which here x is 1, and we will see the same exact outcome portrayed. So I just wanted to show the equivalence of what we're doing compared to this built-in package, because I think it's important to just understand the formulas of what's going on behind the scenes rather than just plugging in numbers and accepting the outcome. So now that we have this type of probability, we can start to think, what is the probability that one or more units are damaged? So we look at everything more than one. And in order to do that, because that would infinitely, we could say that all of them are damaged, we would subtract just the opposite side of that, which is 0 from 1. So think about that area under the curve. We could say 1 minus the probability that none are damaged. So that would be 55. And now we subtract that from 1. So the probability that one or more units are damaged is 44% chance. Next, if we wanted to calculate the mean, variance, and standard deviation, we can just use, rather than, you could make a whole function that creates those different outcomes from the formulas, but you can also just use the different functions from Python to calculate the mean, the variance, and standard deviation, which makes it a little bit more easy. But if we wanted to, I would encourage for the homework, if you wanted to do this approach, or if you wanted to make your own function, that you can go ahead, but both are equivalent if you were to calculate it using your own formula or using these functions. So this will just calculate the mean, which is 0.5, the variance, which is 0.35, and then the standard deviation of 0.59. And we can start to visualize this. I think I wanted to do something else here. I think for this, I just wanted to have I think we just actually want a range here from 0 to how many samples we have plus 1. Apologies for the error there. I'm not sure why I had that there. But this is just creating that range, and we're now going to take this distribution of the hypergeometric and create this probability mass function for it, which creates this random distribution that takes our inputs of what we defined as the variables and creates this distribution for us. And that's really what a lot of the Python packages are doing. It's just creating these random distributions based off of the inputs you give it. And now we can visualize what that would look like. So it's very likely that in this shipment of mangoes that actually only 0 or 1 are damaged, but it becomes a lot less likely for more than that to be damaged. So if you are this QC manager, you can now say that as long as only 0 or 1 are damaged, that the rest are probably fine in your shipment and you can accept it. But if you started to see more, if you saw 3, you might be inclined to open up another box and see if this is just an outlier or is this a consistent pattern, and then you would reject this shipment. So now we talked a bit about how we would calculate it and getting into the math. Again, if you didn't want to use Python, you don't have to. If you just wanted to plug in these numbers into formulas, we use Python to just calculate those outcomes using a function that I defined, that I hand built. But then you can also use Python to leverage the different distributions to simulate what these formulas are generalizing and calculate it that way. And the homework will look very similar to all those different practice problems we just talked through. And in summary, what we discussed today was how to describe random variables and the probability distribution, which built upon what we talked in the last class about mean and variance and standard deviation, and how we're really just trying to see how things tend to outcome. What is the likelihood of seeing the Plinko ball in 6? Well, it might have some variance around that. So we can use this probability distribution to understand these likelihood outcomes under some level of uncertainty of where things will go. And this then extends to different types of probability distributions that we talked about, such as binomial, where we have this true false, and we can now say what's the likelihood of something happening. We think about Poisson, which builds off of that binomial to now say we have this rate of something happening. So what's the likelihood that there'll be 3 people to come into your local Starbucks, and this will then help you know how to inform your staffing for how many people, given the needs to support that likelihood of people coming in. And lastly, we talked about hypergeometric, which is similar to Poisson, but it is used when the independence between samples cannot be guaranteed. And with that, we will conclude the real bulk of this module, because we also talked about how to calculate it using Python. So you will have everything required from this presentation to get going. I have another demo in Python, but this is more just interesting to see rather than necessarily useful for the homework. And I look forward to answering any questions you might have.